Today, we are here to discover the great sun that we all see in the sky, that lights up our day and is the source of life. The sun is not just a celestial object with its dazzling brightness, but also the fundamental basis of our existence. This giant star, which gives us light and life with its endless energy, continues its dance at the center of the universe. In this documentary, we will take a journey deep into the sun and discover its mysterious world full of hot plasma layers, huge energy explosions and magnetic fields. At the same time, we will reveal the effects of the sun on our world and how life is shaped. If you are ready, let's embark on this journey to understand the sun and begin to discover the greatest miracle of the universe. Big Bang is a theoretical concept that represents the beginning of the universe, and the formation of the sun is just one stage of this far-reaching process. In the earliest moments of the universe, there were very high temperatures and energy levels. In this environment, basic elementary particles such as quarks, leptons, photons were formed. As the universe expanded and cooled, elementary particles began to come together to form atoms. This process was dominated by the formation of basic elements such as hydrogen and helium. Atoms came together under the influence of gravity to form galaxies and star systems. Within these galaxies, stars and suns formed in regions such as molecular clouds. The formation of the sun begins with the collapse of a molecular cloud. These molecular clouds are huge clouds of gas and dust, usually containing elements such as hydrogen and helium, as well as other molecules. An external factor initiates a collapse in a particular region of this cloud, causes gas and dust to condense in the center, forming a protostar. The protostar is not yet a full star, but thermonuclear reactions are beginning to occur in its core. The protostar's core increases. Hydrogen atoms begin to combine to produce helium. These thermonuclear reactions lead to the transformation of the protostar into a main sequence star. On the main sequence, the sun continues to produce energy by converting hydrogen fuel into helium. This process can take millions of years. When the star consumes its hydrogen fuel, it expands and enters the red giant stage. It then sheds its outer layers into space, forming a planetary nebula. After the red giant phase, the sun turns into a white dwarf by burning helium in its inner core. During this phase, the outer layers of the star are scattered into space, leaving only a very dense core. The white dwarf cools and extinguishes over time, completing the evolution of the sun. The internal structure of the sun has a complex structure consisting of various layers. We can examine the internal structure of the sun in three main parts. These sections are the core, radiative zone and convective zone. The core of the sun is the innermost region and is where thermonuclear reactions occur. This region can be considered as the main engine that produces the sun's energy. The main element in the sun's core is hydrogen, atoms containing a single proton and one electron. The core of the sun consists largely of hydrogen gas. The temperature in the sun's core is at critical levels required for thermonuclear reactions to occur. Its core temperature is around 15 million degrees Celsius. This high temperature increases the kinetic energy of hydrogen atoms and causes the atomic nuclei to come closer together. Nuclear fusion reactions may have enough energy to occur under this high temperature. The high pressure in the core of the sun allows hydrogen atoms to come together by overcoming the electrostatic repulsion force between their nuclei. This pressure results from the density of the gas within the core and the pressure created by the core's own gravity. Under high pressure, hydrogen atoms come together to form a hot, dense environment that initiates thermonuclear reactions. These high temperature and pressure conditions are necessary for thermonuclear processes to occur, especially proton-proton chain reactions. Temperature and pressure maintain the balance between the thermal energies of hydrogen atoms and electromagnetic forces, so that hydrogen nuclei can approach each other and nuclear fusion reactions can begin. These reactions produce energy by converting hydrogen in the Sun's core into helium. The basic thermonuclear reaction that takes place in the core of the Sun is the proton-proton chain reaction. This reaction consists of the following steps. Two hydrogen nuclei combine by nuclear union to form a deuterium nucleus. A deuterium nucleus combines with another proton to form a helium-3 nucleus. Helium-3 nuclei. When two helium-3 nuclei collide, complete the reaction by producing a helium-4 nucleus and two protons. As a result of these thermonuclear reactions, hydrogen turns into helium and a large amount of energy is released. The energy released during thermonuclear reactions balances the core pressure inside the Sun, allowing it to expand and heat up. This heat is carried from the inner layers of the Sun to the outer layers through radiation and convection and spreads as light on the Sun's surface and into space. Thanks to these thermonuclear reactions, the Sun's core produces energy and provides light and heat for billions of years. The core is the most fundamental region of the Sun's evolution and focused on energy production. The second region we will examine in the internal structure of the Sun is the radiative region. The radiative zone of the Sun is a region where energy is transported from the core to the outer layers, and this transfer occurs mostly through electromagnetic radiation, photons. This region includes the inner layers from the photosphere to the core and constitutes an important stage of the Sun's energy production mechanisms. Thermonuclear reactions in the Sun's core release large amounts of energy during the conversion of hydrogen into helium. This energy creates high-energy radiation of photons within the nucleus. These high-energy photons interact frequently within the nucleus. However, because the plasma inside the nucleus is dense and hot, photons are frequently scattered, absorbed, and re-emitted by free electrons and protons. Photons constantly change direction by interaction with the dense plasma inside. Each interaction transfers some of the photon's energy to surrounding particles. Photons are absorbed by the plasma inside. They can move an electron from one energy level to another, emitting a photon in the process. This is a process by which light transports energy in the inner layers. The radiative zone exists in a state of equilibrium. Photons are constantly absorbed and re-emitted inside. This balance allows the energy produced in the inner layers to be transported to the outer layers and maintain the overall balance of the Sun. The radiative zone is an intermediate region that enables the transfer of energy in the inner layers to the outer layers. This region has a dynamic structure depending on the properties of the plasma inside, such as density and temperature, and the interaction of electromagnetic radiation. This process allows the Sun to produce light and heat steadily, maintaining the overall energy balance. The third region we will examine in the internal structure of the Sun is the convective region. The Sun's convective zone is a region located just above the radiative zone, where convection plays an important role in transporting energy. This region allows the energy produced in the inner parts to be transported to the outer layers. Convection refers to a cyclical movement in which a heated substance expands and rises by becoming lighter, then is pulled back by the cooling substance. In the Sun's convective zone, hot gases rise while cold gases sink downwards. The convective zone, unlike the radiative zone, has lower temperature and density. As we get closer to the surface of the Sun, it is a region where radiative transfer becomes ineffective and therefore convection becomes important. Small cells or spots observed on the Sun's surface are known as granulations, which are a result of convective currents. These formations occur when hot gases rise from the surface and descend downwards. In the inner layers of the Sun, gases heated as a result of thermonuclear reactions expand. These expanding hot gases rise towards the outer layers under high pressure. Then the cooled gases collapse downwards and return to the inner layers. Convection allows energy to be transported when radiative transfer is ineffective or limited. As hot gases rise, they carry the heat they contain to the surface, while cooling gases carry energy from the surface to the inner layers. The Sun's internal structure and convective zone are studied with a technique called helioseismology. Helioseismology provides information about the internal structure using vibrations inside the Sun. The convective zone plays an important role in the Sun's energy transfer, causing phenomena such as granulation. This region maintains the overall energy balance of the Sun by ensuring energy transfer in layers closer to the Sun's surface. Let's examine the atmospheric layers of the Sun. The Sun's atmosphere consists of three main layers, from inside to outside: photosphere, chromosphere, and corona. Each layer has different properties, and there are marked changes in temperature and other atmospheric properties with distance from the Sun's surface. The Sun's photosphere is the outermost layer of atmosphere that forms the Sun's visible surface. The photosphere represents the outer surface of the Sun and is an observable layer. The features observed on the Sun's surface result from events occurring in the photosphere. These features include sunspots, granulation, and other details on the surface. The surface temperature is around 5,500 degrees Celsius or 9,932 degrees Fahrenheit. The temperature of the photosphere arises as a result of the transfer of thermonuclear energy from the inner parts of the core to the surface. Sunspots are relatively cold regions in the photosphere and are usually seen in regions where magnetic activity is intense. Sunspots are areas where intense magnetic field lines are closer to the surface, thus causing the hot gases in the photosphere to cool. Granulation observed in the photosphere is a result of air movements at the surface. Granules are convection cells caused by hot gases rising at the surface and cold gases settling below. These cells divide the image in the photosphere into clusters. Light from the Sun is largely emitted from the photosphere, and this light forms the Sun's visible light spectrum. Energy in the photosphere is produced during thermonuclear reactions within the core and radiates from the surface into space. Magnetic activity in the photosphere is seen as sunspots and magnetic field lines concentrated in certain regions. The formation of sunspots affects gas flows in the photosphere in regions where the magnetic field is closer to the surface. The photosphere represents the observable surface of the Sun and, like most other planets and bodies in the solar system, consists of a hot mixture of gases. Many important aspects of solar energy production and atmospheric events are directly related to events in the photosphere. Another important layer in the Sun's atmosphere, the chromosphere, lies just above the photosphere and contains the red corona that is especially visible during solar eclipses. It is a layer formed under the influence of the Sun's magnetic field. Its temperature is higher than the photosphere, generally ranging from 4,000 degrees Celsius to 50,000 degrees Celsius. The chromosphere is a layer of hot gases, but cooler compared to the corona layer. One of the distinctive features in the chromosphere are prominences. Prominences are pillars of plasma rising from the Sun's surface and shaped by magnetic fields in the chromosphere. The red rays that look like devil arms are caused by the interaction of hydrogen gas in the chromosphere. During solar eclipses, when the Moon covers the solar disk, coronas in the chromosphere become apparent. These coronas are projections of plasma that form under the influence of the Sun's magnetic field and generally extend from the Sun's surface. The chromosphere is a reflection of the Sun's magnetic activity. Magnetic fields cause various phenomena in the chromosphere, especially sunspots and the devil's arms surrounding them. The chromosphere can be observed primarily using solar telescopes and special filters. These instruments allow surveys from the surface of the Sun to its higher layers and observe magnetic activity. Because the chromosphere is located just above the photosphere, it forms the transition zone to the corona, which has a sudden increase in temperature as one moves away from the Sun's surface. Events and magnetic interactions in the chromosphere are important for understanding the general dynamics of the solar atmosphere. The corona, the outermost layer of the Sun's atmosphere, is a region that comes after the photosphere and chromosphere and whose temperature increases unexpectedly as it moves away from the Sun's surface. The corona is a region where the temperature increases with distance from the Sun's surface. Its temperature is around millions of degrees Celsius. This refers to the heating of the corona without energy transfer from the photosphere and chromosphere. This paradox is a problem of solar atmospheric temperature that is not yet fully understood. In solar eclipses, the corona becomes apparent when the moon passes in front of the solar disk. During the eclipse, it forms beautiful crown-like structures above the chromosphere. Since the corona is generally a very thin layer of gas, it is generally considered invisible when viewed from the surface. The corona forms under the influence of the Sun's magnetic field. Magnetic field lines can carry plasma in the corona, causing various dynamic events. It is the source of magnetic interactions such as solar wind and solar flares. The corona is the source of solar winds. Under the influence of high temperature and magnetic activity, plasma particles are constantly released from the corona into space. Solar winds occur when corona particles move rapidly into space and can cause interactions throughout the solar system. The corona zone is the source of solar flares. Conflicts and energy accumulations between magnetic fields can lead to explosions and the release of plasma and energy from the corona to the outer layers of the Sun. Solar flares can interact with the Earth's magnetic field, causing radiation and charged particles to be emitted into space. The corona is the outermost layer of the solar atmosphere and is the main source of solar activity and the release of energy and matter into space. However, the high temperature and other characteristics of the corona raise many questions that scientists still do not fully understand. The reasons for this temperature increase in the Sun's atmosphere are called the temperature paradox. Spots on the Sun are areas that appear as a result of the Sun's magnetic activity and generally appear dark. These spots are associated with the Sun's magnetic field becoming evident on the surface. The Sun consists largely of ionized gases, plasma. In the inner regions of the Sun, different materials form within the core through a process called differentiation, resulting in magnetic fields. The Sun is filled with magnetic fields that act like a spinning ball of plasma during differentiation. Magnetic fields rise from the Sun's interior towards the surface. This increase may cause magnetic fields to become evident on the surface and cause spots to form. As the rising magnetic fields rise to the surface of the Sun, they create distinct and cooler, seemingly dark areas on the surface. These areas are called sunspots. Sunspots generally appear darker because they are cooler than the hot gases in the photosphere. It is usually seen in groups. These groups are a result of magnetic activity on the Sun's surface. Solar activity varies on an 11-year cycle, during which the number of spots increases and decreases. This cycle is known as the solar activity cycle. Sunspots are areas where magnetic fields are intense. This density can cause magnetic conflicts and energy accumulation. Magnetic interactions can lead to solar flares and coronal mass ejections. These events can lead to the release of charged particles into space and increased solar radiation. Solar winds are charged particles that spread from the Sun into space at high speeds. These particles usually consist of electrons and protons, but may also contain alpha particles, heavy ions, and other types of particles. Solar winds originate in the outer layers of the Sun and are constantly radiating into space. It moves from the Sun into space at a speed of millions of kilometers. Their speeds generally range from 400 to 800 kilometers per hour, although higher speeds are possible from powerful explosions. Solar winds become rarefied from the sun into space and generally have low intensity in space. However, their intensity may increase during solar flares or other solar events. They carry a magnetic field due to the charged particles they contain. This magnetic field causes magnetic interactions and plasma flows in space with which the solar wind interacts. Solar winds can affect planetary atmospheres and have the potential to affect magnetic fields. The Earth's magnetosphere can change under the influence of solar winds, causing phenomena such as aurorae, or aurora borealis. Solar winds can cause spacecraft and satellites to be exposed to magnetic fields and interfere with electronic systems. As they spread into space, they drift throughout the solar system. This causes solar winds to affect planets and other celestial bodies in the solar system and to disperse charged particles into space. Solar winds arise as a result of the sun's atmospheric activities and create effects on various celestial bodies in the solar system. Magnetic interactions and energy transfer contribute to a number of natural phenomena caused by solar winds. Let's now examine the effects of solar flares. Solar flares are sudden bursts of energy that occur in the sun's atmosphere, and these explosions can produce various types of electromagnetic radiation. Such explosions occur by emitting high-energy electromagnetic radiation such as X-rays and ultraviolet radiation. This radiation can reach Earth, causing chemical reactions and ionization in the upper atmosphere. This effect can affect the absorption and transmission of radio waves. Solar flares can affect the absorption and transmission of radio waves in the atmosphere. This may cause short-term radio frequency outages in communication systems. Solar flares can cause solar winds and charged particles to interact with the Earth's magnetic field. These interactions can lead to the formation of magnetic storms and visual phenomena such as magnetic auroras. Spacecraft, satellites, and ground-based electronic systems can be damaged when exposed to high-energy particles from solar flares. These particles can cause malfunctions in electronic devices. During periods when solar flares occur, astronauts and airplane passengers traveling in space may be more exposed to high-energy radiation. This could pose a risk to flight safety and space missions. Solar flares can cause signal degradation and outages in GPS systems and communications infrastructure. These effects may be more pronounced, especially at high latitudes and in regions close to the magnetic poles. The effects of solar flares generally depend on the atmospheric and magnetospheric conditions surrounding the Earth. During periods of increased solar activity, these effects may be more pronounced and therefore solar flares are closely monitored. The physical properties of the Sun are the elements that attract attention. The Sun is a large star located at the center of the solar system, and its mass accounts for approximately 99.86% of the total of the majority of other objects in the solar system. The total mass of the Sun is considered to be approximately 1 solar mass unit. Approximately it is around 333,000 quadrillion tons. The Sun's total lifetime depends on how long the hydrogen burning process continues, rather than its current age. Currently, the Sun is an estimated 4.5 billion years old and is in a hydrogen burning phase that will last for an estimated 5 billion more years. When this phase ends, the Sun will transition into the red giant phase. The diameter of the Sun is approximately 1.4 million kilometers. It has a size much larger than the combined diameter of the other planets in the solar system. The density of the Sun is much greater than the density of water, which is a liquid substance, and is around 1.4 grams per cc on average. However, the density in the Sun's core is much higher. The Sun's atmosphere, especially on its surface, contains largely hydrogen, around 74%. Helium is present at around 24%. Other elements, especially trace elements, are present in smaller amounts. Rays from the Sun travel in various regions of the electromagnetic spectrum. The time it takes for the Sun's rays to reach the Earth varies depending on the distance these rays travel. On average, rays from the Sun travel to Earth at the speed of light, approximately 299,792 kilometers per second. The average distance between the Earth and the Sun is 149.6 million kilometers. A beam traveling at the speed of light covers this distance in a few minutes. However, exactly how many minutes it takes varies due to the elliptical nature of the Earth's orbit around the Sun. It takes the Earth 365.25 days to complete one complete orbit around the Sun. Therefore, the time it takes for light to reach the Earth from the Sun varies depending on the Earth's motion around the Sun and at what position that motion is. But in general, this time is around 8 minutes and 20 seconds on average. This time can be calculated based on the concepts of speed of light and astronomical units. One astronomical distance refers to the average distance between the Sun and the Earth. Now let's examine the solar system. The solar system is a system of planets, satellites, asteroids, comets and other celestial bodies orbiting the Sun. The Sun is a giant star located at the center of the solar system. It combines light elements such as hydrogen and helium through thermonuclear fusion reactions, producing large amounts of energy during the process. This energy affects other celestial bodies in the solar system. Large celestial bodies revolving around the Sun are called planets. There are 8 of them in the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. While these planets rotate in their orbits, they also attract the satellites around them. There are celestial bodies called natural or artificial satellites revolving around planets and other celestial bodies. For example, Earth's natural satellite is the Moon. One of Jupiter's large moons is Ganymede. The orbits of the planets around the Sun are generally elliptical. These orbits are defined by Kepler's laws of planetary motion. The orbits of some planets, such as Mercury and Pluto, are more elliptical than others. Planets revolve around the Sun at different speeds. The inner planets, namely Mercury, Venus, Earth and Mars, rotate faster because they are closer to the Sun. The outer planets, namely Jupiter, Saturn, Uranus and Neptune, rotate more slowly because they are farther from the Sun. The Sun is the main energy source that determines the temperatures of the planets in the solar system. The Sun produces a wide range of energy in different regions of the electromagnetic spectrum. These include visible light, infrared radiation and ultraviolet rays. Planets can reflect light from the Sun. This state is called albedo. A planet's albedo determines what percentage of light from the Sun it reflects. For example, if a planet's surface is bright and reflective, its albedo will be high. Planets absorb some of the light from the Sun. The type, color and composition of the material on the surface affects its ability to convert this absorbed energy into heat. The planet absorbs energy from the Sun and then loses heat by radiating that energy back into space. This process is an important mechanism that maintains the temperature balance of the planet. A planet's atmosphere can absorb light from the Sun and retain heat or reflect some of it back into space. This has a large impact on temperature depending on the planet's atmospheric conditions. The Earth's average surface temperature is generally estimated to be between 14 and 15 degrees Celsius. However, this value may change over time and be affected by factors such as global climate changes. Neptune is one of the ice giant planets in the solar system. Neptune's atmosphere consists largely of hydrogen, helium, and some methane. These gases affect the temperature of the planet. However, since Neptune has no internal heat sources, it is heated largely by rays from the Sun. Since it is located at a very far distance from the Sun, its surface is cold. On average, The temperature in Neptune's upper atmosphere is around -214 degrees Celsius. However, this value varies depending on different layers of the atmosphere. Asteroid belts include a series of small celestial bodies located between Mars and Jupiter in the Solar System. These objects are usually rocky or metallic and revolve around the Sun. The Kuiper belt is another collection of small objects located in the outer regions of the Solar System. This belt contains relatively smaller objects, dwarf planets and comets. The Oort Nebula is a hypothetical region of distant, cold celestial bodies located at the theoretical boundaries of the Solar System. These celestial bodies in the Solar System rotate in their orbits around the Sun. The Solar System has been subjected to billions of years of evolutionary processes, during which planets, satellites and other celestial bodies have formed, evolved and come together. Exploration and understanding of the Solar System are among the fundamental topics in astronomy and space sciences. Space exploration has helped us better understand the Solar System and investigate questions about the existence of life in the universe. The Sun affects the planets, satellites and other celestial bodies around it through its gravitational force. Gravity is a force on which the mass of one object acts in proportion to the mass of another object and the distance between them. Isaac Newton's law of universal gravitation expresses this interaction mathematically. The gravitational interaction between the Sun and a planet or its satellite occurs around the gravitational center of the two bodies. The gravitational force is directed towards this center. Because the Sun orbits the planets, the movement of a planet or satellite usually occurs in an orbit shaped like an ellipse. This ellipse orbit is determined by the gravitational interaction of the planet or satellite. Kepler's laws, which emerged as a result of Johannes Kepler's studies on planetary motion, state that planets rotate in elliptical orbits and scan equal areas in equal times. These laws are used to explain planetary motions observed in the Solar System. According to Newton's third law of motion, as the planets attract the Sun attracts the planets. However, because the Sun has a much greater mass compared to the planets, the Sun's influence is often more pronounced and dominant. Albert Einstein's theory of general relativity explains gravity in a more comprehensive way. This theory proposes that gravity causes objects to curve the fabric of space-time. That is, when an object falls on another object, this fall actually results from the curvature in space-time. These curvatures determine the orbits of the planets around the Sun. General relativity also includes the effects of gravity on time. Time runs slower near a high-mass object. This provides more precise results than classical gravitational theory for calculating the orbits and motions of planets around the Sun. Precession, which causes planets' orbits to rotate over time. Precession is a phenomenon in which a planet's orbit rotates slowly, caused by gravitational interactions warping the fabric of space-time. These principles help us understand the movements and positions of celestial bodies in the Solar System. Gravitational interactions determine the orbits of the planets and the positions of other celestial bodies within the system. The role of gravitational force in the evolution and structuring of the Solar System is of great importance. The Sun is located in one of the spiral arms that form the Orion Arm in the Milky Way galaxy. This is a general description of the Sun's position within the galaxy. More specifically, the Sun is on the arm of Orion, slightly out from the interior of the Milky Way. Milky Way galaxy is complex as it is a barred spiral galaxy and includes various structures within the galaxy such as stars, gas and dust, spiral arms and bars. The Sun is located on the Orion Arm within these structures and rotates around the galaxy in a cycle in this arm. Therefore, the Sun's position within the galaxy is generally over the inner regions of the Milky Way. However, A detailed analysis of its motion within the solar system and its more specific location within the galaxy requires long-term observations and modeling studies by astronomers. Research on this subject helps us better understand the structure of the Milky Way and the movements of the stars within it. It is considered to be approximately 149.6 million kilometers. This average distance varies across the elliptical orbit between the Sun and the Earth, so this value refers to an average value called the semi-major axis. Since the Earth's orbit around the Sun is elliptical, there may be points where we are sometimes closer to the Sun and sometimes farther away. This situation is called perihelion, or the point closest to the Sun, and aphelion, or the point farthest from the Sun. Perihelion occurs in early January and aphelion occurs in early July. The Sun rotates around itself on an axis. This rotational movement is called rotation around its own axis, or solar rotation. The Sun's axial tilt is relatively small. A solar period refers to the time it takes for the Sun to complete one complete rotation around itself. While the Sun rotates faster in the equatorial region, its rotation speed decreases as it approaches the poles. This is known as differential rotation of the Sun. The Sun completes a full rotation around itself in approximately 25 days due to its rotation speed in the equatorial region. At the poles, this rotation period is approximately 35 days. This rotation of the Sun around its axis is different from the rotation of other objects in the solar system. For example, the Earth rotates approximately every 24 hours to complete its rotation around its axis. The rotation speeds of planets and other bodies in the solar system vary depending on whether they are closer to the Sun or more connected to the Sun. Now let's examine solar eclipses. Solar eclipses are events that occur as a result of the correct alignment of the Sun and the Earth on the Moon's orbit. A solar eclipse refers to a situation in which the Moon partially or completely covers the Sun. This event occurs when the Moon comes between the Earth and the Sun, blocking the Sun's light. There are two basic types of solar eclipses. A partial solar eclipse refers to a situation in which the Moon only partially covers the disk of the Sun. At the observing location, the Sun appears half-covered. Such eclipses can often be observed over a wide geographic area. A total solar eclipse refers to a situation in which the Moon completely covers the Sun. In this case, the Sun is completely covered at the observing location, creating a shadow cone, which is a dark region. However, total solar eclipses are limited to a specific geographical area and can usually be observed over a narrow band. Solar eclipses can be observed within a specific geographic area and can often be calculated in advance. Due to the tilt of the Moon's orbit and the tilt of the Earth's orbit, solar eclipses recur at certain time intervals. These events occur when the Moon is in the new moon phase. It is often recommended to use sunglasses or special solar filters to view solar eclipses. Looking directly at the Sun can seriously compromise eye health. During solar eclipses, temporary interruptions in shortwave radio communications may occur due to changes in the ionosphere in the upper atmosphere. During a solar eclipse, observers on Earth can observe whether the solar eclipse is partial or total in a particular geographic area. Solar eclipses are events that generate great interest among astronomy enthusiasts and the general public. Stars outside the solar system may host planets in their systems, and these planets may have various properties. Sun-like stars are stars that have properties similar to the Sun, and their evolution can occur in a manner similar to the Sun. Stars are often found in star systems. These systems may contain one or more stars, planets and other celestial bodies orbiting them. Stars are classified according to spectral classification. In this classification, stars are classified based on their surface temperature and color characteristics. Many stars outside the solar system are stars with low mass and temperature, such as red dwarfs. Red dwarfs make up a large portion of the stellar population. High-mass stars can become giant stars or supergiant stars in their evolution. These stars can often be much larger and brighter. Sun-like stars are stars with mass, temperature and properties similar to the Sun. These stars may undergo a similar process to the evolution of the Sun. An example of these stars is TEU Ceti star can be shown. Located 11.9 light-years away, this star has a spectral class similar to the Sun. Taurus. A number of planet candidates have also been discovered orbiting Ceti. The Sun, which illuminates our world, will complete its life cycle in the future. Once the Sun has largely exhausted its hydrogen-burning process, it begins to expand in its outer layers and the thermonuclear reactions taking place within it change. This phase is the red giant phase of the Sun. As the Sun converts hydrogen into helium, the weight of the helium accumulated in the center increases. This increases the temperature and pressure in the center. Increasing pressure causes the hydrogen in the outer layers to expand. The Sun expands its outer layers and slowly begins to lose its atmosphere. During this expansion, the Sun becomes larger in volume but does not lose mass. The red giant phase is this period of expansion of the Sun, a phase that will last several 100 million years. During this phase, the Sun will slowly shed its expanding outer layers into space. The final end of the Sun begins at this stage. After the red giant phase, the Sun begins to burn helium inside. When the hydrogen runs out, the helium burning process in the center begins. The Sun throws its outer layers into space as an atmospheric shell during the burning of the helium inside. This ejected material forms a brightly colored shell called a planetary nebula. After losing its outer layers, the Sun's core turns into a white dwarf, a hot core composed of helium and other heavy elements. The white dwarf is very dense in terms of specific mass but has a similar size to the Sun in terms of mass. The white dwarf cools over time and becomes less bright. Over billions of years, the white dwarf decays into a cooler form called a black dwarf. These final stages of the Sun's evolution are a process that takes billions of years. These phases may vary depending on the mass and structural properties of the star. However, during this evolutionary process, the Sun will complete its cycles and turn into a white dwarf. Don't forget to subscribe for brand new documentaries and more scientific content.